So we're talking about number 17. And if I was standing above the door, then what I would see in regards to the door is a bar. And I can treat the door as a bar rotated about one end. Doesn't matter that the door is actually really thick, because when we consider a point, say, here in the middle of the door, that mass represents all the points that are this far away from the axis of rotation. So whether the door is really, really thin, just a bar at the very top, or is this long, extended object, because the axis of rotation is placed the way it is, I can treat this as the moment of inertia of a rod rotated about its end, which we did prove in class is 1/3 ml squared, where this represents the length of the door, or how wide it is, and m is the mass of the entire door. And this will be true for all of our objects and all of our shapes. Whether it's a thin disk or a thick disk, it still rotates with the same moment of inertia about its center, mr squared, 1/2 mr squared, because again, the extension part doesn't matter since those points are the same distance away from the axis of rotation. Now, that being said, what we don't have is an easy way to talk about an axis like this. Because although if you looked it up in the book, you know that they gave you the moment of inertia about the end, and they probably gave you the moment of inertia about the middle. That's it. So what I'm about to tell you is something that needs to be in all of your notes. It was going to be part of what we talked about today anyways, but we might as well get it in here. Something called the parallel axis theorem. The parallel axis theorem is a way to move the axis around in an object without having to totally recalculate the moment of inertia. And I've never proved it myself, so as a theorem goes, I'm sure there's a proof out there online, and you eager people who really care about that can go look it up. I just don't care enough. And if you do go look it up and you get all excited about it, I don't need to see it. I have Wikipedia. If I care, I'll look it up. The actual theorem is pretty easy. There are some things to pay attention to here, but it's pretty easy. It says that the moment of inertia through a parallel axis will be equal to the moment of inertia through the center of mass plus this value representing the shift of the moment of inertia. X is how far you are shifting the moment of inertia from the center of mass to the new axis of rotation. There are some caveats here, but is everybody okay with that so far? So in this one, the door is 91 centimeters wide. And we're shifting it 15 centimeters from one edge. If I wanted to use the parallel axis theorem, X would be this distance. The distance from the center of mass to my new axis. And I'd have to use the moment of inertia of the center of mass. Everybody okay with that so far? Any questions about that? Now, the parallel axis theorem is great because it saves you the indignity of having to redo what could be a complicated integral calculation, especially for situations in which you can no longer use symmetry. Imagine this arrangement. So for those of you who were in class last week, we did a disk. Or at least we did it in a couple of classes. I don't know if we did in this one or not. The moment of inertia of a disk through its center is 1/2 mr squared, where r is the radius of the disk and m is the mass of the disk. Now, if I want to rotate about its edge, like right here, like I'm going to take a Frisbee and kind of flick it off the edge of my thumb, that'd be rotating about its edge like this. Well, that'd be a hard moment of inertia to calculate. When we did the disk calculation in class, we had the benefit of knowing that all of our mass pieces were all, the same kind of distances from the center. This would be difficult to use as our starting point. Trying to point to each and every mass would be hard, I think, when I have to be at the edge like that. It was not hard to point at each piece of mass when I was at the center, because I could start from the center. Each piece of mass is along some radius from the center. But the parallel axis theorem works just fine here. If I want to use the parallel axis theorem, I center of mass plus I'm going to shift it 1 radius. That's all I'd have to do to figure out the moment of inertia. I'm going to shift it from the center to the edge. That's a lot easier than doing all that integral stuff, isn't it? Now, that part's not so bad. But there's huge limitations. And one of the huge limitations is you can't suddenly take this thing and spin it this way using the parallel axis theorem. Like take a coin and spin it on its edge on the desk. That moment of inertia I can't get from the parallel axis theorem, because that's causing me to rotate the axis 90 degrees. It's called the parallel axis because the axis that you are choosing has to be parallel to the axis you already have. That's why it's called the parallel axis theorem. All right, does that get you a good start on number 17? All right. Anything else in the homework you want me to get you started on? All right. Then today, we're going to talk about something else. And I want to talk to you about torque. And there'll be some side discussions too, but so I do believe with my little door exercise right there that most of you understand the nature of torque. The goal of the torque is to cause something to rotate, to change orientation, to spin. That's the goal of a torque. And so when we apply a torque, there are 3 features of that torque. And although I'm going to draw them in 2 dimensions, please be aware that there's a 3-dimensionality to this. I'm just not going to be able to put it up here. Using the door as my example, the drawing has to involve a couple of things. First, I have to put something on the drawing for us to indicate where the axis of rotation is, or the pivot point. There's a number of words that can be used to describe the pivot point, but generally the symbology tends to be a small triangle to indicate the pivot location or the axis. Up until this point in the year, we've assumed that applying a force to an object applies it to the center of mass. We've never assumed that the object had any extension. Well, that has to end right now. From now on, where you apply the force actually changes the nature of the problem. And we're going to approach this slowly, but some of you know that if you push too high on a box, you'll cause the box to fall over. So we've talked not about that. We've assumed that when you apply a force to a box, it's just at the center. We just draw the whole thing as a dot, and we just say, okay, there's forces this way, this way, this way. No big deal. Not true now. Our objects have extension. Where we apply the force matters. And not just where, how we apply that force matters. So we know that there are 3 things involved. And I don't think this is going to be hard to understand, but I'm going to draw the force first. So there's the fact that you are applying a force.
I'm having trouble. Sorry.
Yes, you are, sorry. You have to apply the force first. So I'm drawing the force. I am drawing it as an arrow because force is a vector. Now we have to add something that we haven't talked about before. There's where on the object the torque is applied. This is an arrow drawn from the pivot point to the point of application of the force. It's drawn from the pivot point to the point of application of the force. We're going to use a lowercase r for this. And please stop calling this radius. I mean, a lot of people do, but it's not a radius. We use r for a lot of things, if you've noticed. And the fact that this is involved with spinning makes you think radius. And it could stand for a radius in some cases. But this is the torque arm or lever arm. A longer torque arm allows you to gain more leverage when you're trying to rotate something. You've used the word leverage before. But the last piece is this angle. Now, the angle at which you apply this force also matters. I don't think I need to say this, but whether I draw the force on that side or I draw the force on that side, it's the same. Wouldn't matter. This angle would also be the same angle. So don't get too worried about where the force is drawn. We use the lowercase Greek letter tau for torque. It's about the size of a lowercase t. So that kind of gives you a good comparison about how tall you should make the tau character. So a capital T would be taller than that character. So lowercase t about the same height. So it's like somewhere in the middle for height. Greek letter tau for torque. And it is a vector. And we describe it as a special kind of product because the force and the torque arm are also vectors. So this is a vector product. We talked about two kinds of vector product, or one kind of vector product before. Work was a vector product. When we calculated work, we took two vectors, though, and produced a scalar. The goal of work was to find out how much of the force was in the direction of motion. We used cosine. For torque, our force is more effective when it's perpendicular. So if you want to find out how much of your force is actually causing torque, we want to know how much is perpendicular. So we're going to use sine. This is called the cross product. So we use a cross here, but it's also a type of vector product that leaves you with a vector. Our answer has direction. The resulting torque is trying to open the door outwards, not inwards. So our torque, in the case of the door, is supposed to be downwards through the hinge. Right? We want the door to open outwards. So we want a torque that is downwards through the hinge. This part's going to be a little more difficult for you to understand. But whether you acclimate to this or not, there needs to be a way for us to find the direction of a torque from the direction of the torque arm and the force. I mean, drawing this picture, I hope it's all pretty obvious. That's the direction that torque's going to cause the object to spin. But it has to be more than just obvious. There has to be a mathematical way of indicating the positivity or negativity of the torque. And I have to be able to do it without seeing a picture. That's the problem. So there's a mathematical way to do it. And for people who are involved in more experienced math, usually involves a matrix, and the matrix calculation is not hard. It involves determinants of a matrix in calculating torques like this. For those of you who will go on in math, there's a method there. And for programmers, you'll be doing that a lot. You guys are interested in video games in any way, shape, or form. All 3D worlds involve the manipulation of vectors. So whether you're playing Fortnite or you're playing, pick your game, if it's generated on a 3D world, they use vectors to describe that world. In fact, today ray tracing is all the rage because a lot of video cards can do ray tracing live on the video card. Ray tracing is exactly this, looking at the way vectors interact. So there is a method for doing this mathematically, but also there's a right-hand rule for it. And I want to talk to you about the right-hand rule for the cross product. And this is a different right-hand rule than what you've been. And although I like the right-hand rule as a method goes, because it's, it's kind of fun to do that. The textbook will also say that, well, you could do it using an X, Y, and Z coordinate system too. And they have a method like this in the book for X, Y, and Z. They make the third one. And I don't know if I did this in class, but we talk about the symbology you use for into and out of the board. So the default is out of the board, is positive. So their method is to say, if R is this way, then it's negative. If F is this way, then it's positive. R times F is negative. So my torque has to be negative. Right? Because the R pointed in the negative direction and the F pointed in the positive direction. The problem is that always assumes that you have a coordinate system available for your problem and that out of the board is always positive. You always have a right hand with you. So I always feel like you can always figure out the direction of your answer using your right hand. You don't always have a coordinate system available. You'll have to make one up that is in perfect agreement with what the problem wants you to do. That's harder. So if you like the book's methods, feel free, read the book. It'll give you the right answer every time. I'm going to continue to use the right-hand rule as a matter of course in this class. All right, quick sum up. That's how you calculate torque. It's going to come down to this most of the time. And the most effective torques are when the angles are 90 degrees. Now, you have torque questions where they're definitely all over the place with direction and force. Don't be too, there's like a picture like this where they have a box and they say to you there's a force this way and a force this way, and the pivot point is here. So this is one of the questions. I probably assigned this question. At least I would have wanted to. One of these forces doesn't cause a torque, and one of them does. So this force doesn't cause a torque. You can look at it for two reasons why it doesn't cause a torque, but the most important one is the angle between the torque arm and the force is 0 degrees. Right? If the torque arm is drawn this way to where the force is applied, and the force is right back along it in this direction, well, then the angle between the torque arm and the force is 0 degrees. It doesn't cause a torque. But also, just look at it. It's pointed directly towards the hinge. Is there any way for any component of that force to cause the system to turn? No. Now, this one does cause a torque. And it causes a torque that's out of the board. Do you see why? Torque arm is from here to here. That's the torque arm. If I do my right-hand rule, torque arm this way, force upwards. Just trying to get to turn like that. So the torque is out of the board. That's pretty straightforward. I don't think there's a lot there. The thing about torque, though, is that it's an extra step. If you're noticing, when we did force, the worst or the most we had to do to find a force was maybe mg. Maybe we had to do something complicated because of friction. But generally, forces were forces. Torques aren't like that. If you want to use torque, you've got to calculate the size of that torque. And that involves a torque arm, a force, and an angle. You can have lots of torques acting on an object. Therefore, dynamically, there's the possibility of the net torque equaling 0, a statics problem, or the net torque causing an acceleration. Now, this shouldn't be a huge leap, but if the net torque causes an acceleration, this isn't going to be MA. I think you guys probably know this is going to be I alpha. MA would be for something that's moving translationally. I alpha is for something that's going to rotate, which suddenly means that not only do you have to do this every single time there's another torque, but you also have to know what the shape of the object is and find its moment of inertia. Rotational motion is all the same things as linear motion, but each piece requires a lot more thought to deal with. And that's why I think rotational motion is hard for a lot of students. Because now you've got to do this for each one of your torques. You've got to figure out what the shape of the object is. See if you have to shift the axis of rotation for that shape that you're causing a rotation on. And then from there, maybe figure out what the acceleration is. A little bit more little stuff. I didn't say this, but I think you probably need to hear it. The units will be meter Newton. And it's in that order on purpose. Newton meter is generally considered joules. We get that from work. And although meter Newton are the same units in a different order, we leave them in that order on purpose to convey that that's a torque. So anybody who has a torque wrench at home probably knows. Does anybody have a torque wrench at home? You know, the tool to measure torque when you're wrenching something. Oh, well. My torque wrench is in foot-pounds, but has a little set of things on the inside of it that tell me meter newtons. Most torque wrenches are for working on cars. You don't want to over-torque a nut, or else you'll have a problem with whatever you just torqued. It won't be able to do what it's supposed to do. Probably the only nut that you guys tend to have on your car that you undo all the time might be the lug nuts on your car. Has anybody had to change the tire of their car before? Or did you just call some guy to do everything in your world? It must be nice to live in your world. Gaining more leverage generally is getting a larger wrench in order to cause a nut to turn. So please consider that these kinds of words are almost always related to rotational motion. We'll use meter Newton though. That's generally what I want to use here. So let's take a look at a particular problem. I'm not going to do a homework question because you'll have a chance to do all those. Let's take a look at a simple kind of idealized problem. The meter stick I've been using as an example has a hole in one end where I could hang it from that hole. So if I were to tie a string on the meter stick and hang it, like from the ceiling, and were to just release the meter stick, would you guys agree that The one end would swing downwards. Okay. What you might not think, and I want you to think about all of this, is that the meter stick is experiencing two forces, not one. There's the obvious force I hope that all of you are seeing must be there. And that's got to be the force of weight acting on the center of mass. That has to be there. But there's also a string connected to the meter stick, which means there also must be a tension force upwards. Now, you might not believe this, but when you first release it, the net force is likely zero. Tension upwards and weight downwards will be balanced. It won't stay like that, because as the thing starts to travel in a circular path, that's going to require more tension to hold it in place. But the net torque is not zero. Because although there's two forces acting on it, the tension acts at the likely pivot point. And because it acts at the likely pivot point, the torque arm length for the tension is zero. So it applies no torque. The weight, on the other hand, does apply a torque. And the torques are unbalanced, so I alpha. The meter stick will begin an angular acceleration, but the center of mass and the meter stick as a whole doesn't have a translational acceleration. Meaning the meter stick won't fall to the ground, it'll begin to rotate about its pivot point. Of course, there's every reason to believe that you guys could probably do this. If this is length L and the torque arm is L over 2, size of the force is mg, sine of 90 degrees. That's the left side of torque. At the same time, moment of inertia, 1/3 ml squared. It's being rotated about one end, and we talked about a bar rotated about one end, times alpha. I think you could calculate the acceleration of the system the instant it was released. But I chose this problem because I want to show you something important. I could ask you about the moment it was released. That question isn't so terrible. But as it swings downwards, do you realize the torque isn't constant? If you're not realizing why, then maybe look at this picture. After it's rotated for a little bit, mg is not going to change. The size of the force is the same, but the angle's changing. This problem's tough. Really tough, actually. This might be a complicated question. So although we can talk about torque and we talk about acceleration, our problems are going to become more dynamic. We need to be thinking about how the orientation of the object changing affects how these forces are acting on the object. It wasn't like it was before, where the forces just act on the center of mass and the object goes about doing what it's going to do. Push on a box. What kind of forces are acting on the box? I can think of 4 forces that act on the box. If you can't, then think about all the possibilities here. Name one. friction is likely acting on the box. I would think friction is going to act this way. Name something else? Definitely going to be weight. I'm thinking center of mass of the box, perhaps. Something else? Yeah? The normal force? That acts on the bottom of the box. I'll draw a little offset. And? Yeah, the guy pushing on the box. I'm assuming he's pushing with more force than there is friction. But do you notice, although there are 4 forces here in this diagram, they all act with different torque arms and different directions. I might be able to figure out what the acceleration of the box is, but it is quite possible we could push the box over. Right? Especially if we hit like a little bump here. You hit that bump, it's probably definitely going over. Wouldn't you agree? That's why you don't push so high up on the box. You probably learned that lesson the hard way when you were little. You know, some toy your parents gave you that you toppled over and made funniest home videos. And you learned your lesson that time. And you've probably come to grips with, I need to push lower on objects. That's why every one of the TV carts in this room still has the warning that the TV is really heavy and it's on top of the TV cart. Even though there's no more TV carts, the warning labels are still on the carts. Because kids will be pushing the TV cart and push it right over. Why? Because all the weight's on the top of the cart. You start shifting this sucker higher up, bad things happen. So we won't go into most of these problems. These are pretty challenging dynamic questions, but we will take a look at some of them. All right, that's a good introduction.